Hello, this is the second lecture for eco420W. And last week, in the previous lecture, I reviewed the basic concepts of probability framework. So we learned what is the population, and what is the random variable, and what is the distribution. And then we reviewed what is the mean and what is the variance and the standard deviation. So let's so this is we also learned skewness and kurtosis as an extension of that expectation. So now, but these are mean, variance, standard deviation, skewness, kurtosis are all about one variable. They are defined for each of the variables. So none of them captures the relationship between multiple variables. So we have to define another measure for the relationship between variables. And to understand the relationship between random variables, first we have to think about a joint distribution. So joint distribution is simply the distribution that characterizes two random variables at the same time. For example, what is the probability that x is smaller than 0 but z is greater than 1 at the same time? So when a probability describes two random variables at the same time, then we say that is a joint distribution. Joint distribution of x and z, for example. And so joint distribution is probability distribution, and covariance is a numerical measure. Covariance is one number. So covariance is defined in this way. Covariance between x and z is the expected value of x minus x mu x. So this is the deviation of x from its mean, its center. And z minus mu z is the deviation of z from its mean. So if you think about a scatter plot, where was it? If you think about scatter plot, so x, if you think like assume that the horizontal variable is x and vertical variable is z, then deviation x is a kind of horizontal deviation, and a vertical deviation is for z. The z deviation is a vertical deviation, and x is a horizontal deviation. So you multiply those deviations and take expectation of that. It is a measure of the linear association between two variables. So when x, say you can think it this way: when x increases, when the horizontal deviation is positive, and at the same time if the vertical deviation is also positive, then their multiplication will be positive. But when x deviation is positive and z deviation is negative, their multiplication is negative. So when you multiply them, you may just focus on their sign. If if the multiplication inside the expectation is positive, that means there is a tendency that when x increases, z increases too. So it's kind of moving together. But when the multiplication is negative, that means when x increases, z decreases. So they are moving in the opposite direction. And so expectation is just the average sign, whether the sign is positive on average or negative. So in that sense, the covariance captures how two variables are related to each other. Simply, when x increases, if z increases too, then the covariance will be positive. And if not, if when x increases, if z decreases, then the covariance will be negative. The problem here is that it's not unit free. So it's not unit free. It's a little bit, it makes the that measure a little bit less convenient to use. Because, for example, when you multiply 10 to x, then the covariance will be also multiplied by 10. So, for example, when you change uh, pounds to ounces or inches to foot, like so, when you change the unit, then you have to multiply a certain number. Then every time the covariance will change, which is very inconvenient because changing the unit does not change the nature of the random variable, but the measure changes, which is not desirable. So so we are going to modify the covariance to a correlation coefficient in the next slide. And as I said, positive covariance implies positive relationship, so they are moving together. And if an x and z are independent, they are statistically independent, then the covariance will be 0. But zero covariance does not imply independence. I'm going to show you a counterexample in a couple of slides. So, but it's intuitive. When x and z are independent, they are not correlated with each other. So, obviously, the covariance must be 0. And it's interesting to see that the covariance, if you try to calculate the covariance of x and x itself, so, or you may think that you define a random variable z, exactly the same random variable of x. So z equals to x. That's your definition. Then what is the covariance? It simply becomes the variance of x. So when you try to calculate the relationship between me and myself, then it is the variance. So the variance is mathematically a special case of covariance. So covariance is a more general measure than the variance. Okay, then back to the example. Here you see a negative trend. So the trend, if you imagine a straight line going through the dots, then it's clearly downward sloping, which means when student-teacher ratio increases, the tendency is that the test score drops. So there is a downward sloping relationship, which implies a negative covariance. I think it's typo. I'm not so sure. I don't calculate the data, but anyhow, the covariance should be negative. Covariance should be negative, and if you calculate the correlation coefficient is minus 0.23. That is defined this way. So correlation coefficient is a standardized covariance. So standardized covariance is the correlation coefficient. Because we need standardization because, as I said, when you change the unit of x or z, the covariance changes. So it's inconvenient. We would like to prevent that problem and make a measure which is unit-free. Then a simple idea is to standardize the covariance. So covariance is sometimes denoted as sigma x and z, which means covariance between x and z. You divide the covariance by the product of two standard deviations. So you are handling two random variables. So use both standard deviations to standardize the covariance. Then you have a correlation coefficient R of x and z. And as a result, after the standardization, the correlation coefficient is always greater than -1 and smaller than 1, right? So it's now unit-free. No matter, even if you multiply a large number, still it does not go over 1. So always it is the unit is -1 to 1. The scale is fixed. And think about some special cases where correlation is 1, which means there is a perfect positive linear correlation. So if correlation equals to 1, then you see a line in the scatter plot. So all the dots will make a perfect line. That is when you get correlation equals to 1. Negative 1, excuse me. So when correlation is negative 1, you will see a perfect line downward sloping. Positive 1 is from the case where the dots make up a perfect line aligned in a perfect straight line upward sloping. So these perfect line is either from correlation positive 1 or negative 1, depending on the slope. And correlation 0 means the trend line is flat or vertical or no trend line. So this is correlation equals to 0 means there is no linear trend. No, when x moves, there is no impact on z. That's basically what correlation 0 means. Graphically, so this is what you get when correlation is positive 0.9. So positive 0.9 is very strong correlation, and negative 0.8 is also strong but weaker than this one in absolute value. In the absolute value, this is stronger and it's a little bit weaker than if you compare both. And also the different signs imply different slopes, right? Increasing and decreasing. And this is an example of zero correlation. There is no pattern. When x increases this direction, well, I don't know what happens in y. There is no clear pattern. By the way, another problem here is, so in this case, in the last case, there is a when you look at the graph, there is a clear pattern. So when x increases, y first increases, and then after a certain point, it starts to drop, and the drop rate becomes faster. It drops even faster as x increases. So it's a quadratic function, like a quadratic function. The problem here is that the correlation coefficient and the covariance cannot handle nonlinear pattern. So it is nonlinear. So slope increases and then becomes slower and then flat and drops quickly. This kind of nonlinear pattern is not captured by the correlation or covariance. This is why the other way, the converse is not true. Even if covariance is 0, but that does not imply x and z are independent. So when covariance equals to 0, that only implies that there is no linear relationship. But there may be some relationship which is nonlinear, like quadratic or anything like whatever, like exponential function, sine, cosine functions, or logarithm, or whatever. There may be different shapes of functions which is nonlinear. Then covariance cannot handle that. That's why the converse is not true. Okay. I will continue. I will talk about another measure in the next video. Thank you.